Hey everyone, welcome back to Quant Prof. In this video, we will solve 10 quant interview questions that become progressively more challenging. Visit quantprof.org for more quant interview resources. 3 ants are positioned on the 3 vertices of an equilateral triangle. Each ant randomly chooses one of the 2 adjacent vertices to move to, with equal probability. For example, this ant moves to one of the green vertices with equal probability. What is the probability that 2 ants end up at the same vertex? Pause the video here if you want to give it a try. Here's the solution. First, let's compute the probability that no 2 ants end up at the same vertex. For that to happen, all the ants must move in the same direction, either all clockwise or all anti-clockwise. Each ant moves clockwise with probability 1 by 2. Since the ants move independently, the probability that all 3 move clockwise is 1 by 2 cubed, or 1 by 8. Similarly, the probability that all 3 move anti-clockwise is also 1 by 8. So, the probability that no 2 ants meet is 1 by 4. Therefore, the probability that at least 2 ants end up at the same vertex is 1 minus 1 by 4, or 3 by 4. Alright, let's move ahead to the next problem. We begin with a fair die showing 1. Every minute, we flip a fair coin. If it lands heads, we leave the die as it is. If it lands tails, we roll the die. After 5 coin tosses, what is the probability that the die is still showing 1? Here's the solution. Suppose we do not get any tails. The probability of this case is 1 by 2 raised to the power 5. In this situation, we never roll the die, so it will still show 1 for sure. Now consider the case where we get at least 1 tail. The probability of this case is 1 minus the probability of the first case, which is 31 by 32. In this situation, the die is rolled 1 or more times. Therefore, the final face of the die is equally likely to be any number from 1 to 6. So the probability that it shows 1 in this case is 1 by 6. Using the law of total probability, the required probability is 37 over 192. Now the next problem. We have 3 marbles colored green, red, and green, placed in that order in a row. In one move, 2 marbles are randomly selected and their positions are swapped. For example, in the first move, we can select these 2 marbles and swap their positions. Then, in the second move, we could select these 2 marbles and again swap their positions. This process continues in the same manner for all subsequent moves. Initially, the order of the marbles is green, red, green. What is the probability that after 20-25 moves, the marbles remain in the original order? Here's the solution. Let P denote the probability that the marbles remain in their original order after 20-24 moves. So, the probability that the marbles are not in their original order after 20-24 moves is 1 minus P. Let's see what happens if the marbles remain in their original order after 20-24 moves. If these 2 marbles are swapped, the marbles will remain in their original order. However, the other 2 possible swaps will change the order. So, if they are in the original order, the probability that they remain in the original order is 1 by 3. Similarly, if the marbles are not in their original order at the end of 20-24 moves, swapping these 2 marbles will restore the original order. On the other hand, the other 2 possible swaps will not restore the original order. So, if they are not in their original order, they will return to the original order with probability 1 by 3. So, using the law of total probability, the probability that they are in the original order after 20-25 moves is given by this equation. This term represents the case where they remain in the original order after 20-24 moves, while the other term represents the case when they are not in the original order. Therefore, the required probability is 1 by 3 as P cancels out. Let's move on to the next problem. The numbers 1 through 100 are written on a board. Alice and Bob play a game using these numbers, taking turns alternately. On each turn, a player fills an empty space between 2 numbers with a plus, minus, or multiplication symbol. Alice wins if the final result is odd, and Bob wins otherwise. If Alice goes first, who has a winning strategy under optimal play? Alice has a winning strategy. On her first move, Alice fills the gap between 1 and 2 with a plus sign. Now consider the numbers in this blue block. The odd numbers in this block are 3, 5, 7, and so on till 99. Each of these odd numbers has gaps on both sides. Whenever Bob places a symbol on one side of an odd number, Alice can place the multiplication symbol on the other side of that odd number. This ensures that every odd number except 1 has a multiplication symbol on at least one side. As a result, the expression in the blue block is even, and therefore the entire expression is odd. Let's move on to the level 6 problem. We have an n by n grid, and some of the cells are infected. For this problem, We will consider two cells to be adjacent only if they share a side. Diagonally connected cells will not be treated as adjacent. In each step, all the cells that have at least two adjacent infected cells get infected. Is it possible to eventually infect the entire board if we start with fewer than n initially infected squares? If not, prove it. If yes, provide an example configuration. Pause the video here if you want to give it a try. Here's the solution. Note that the perimeter of the infected region always either remains the same or decreases. For example, suppose a cell with two adjacent infected cells becomes infected. In this case, the perimeter remains the same. If a cell with three adjacent infected cells becomes infected, the perimeter decreases. If a cell with four adjacent infected cells becomes infected, the perimeter again remains the same. So, we conclude that the perimeter of the infected region either remains the same or decreases over time. Initially, if k blocks are infected, the maximum perimeter is 4k. To infect the entire board, the perimeter would need to increase to 4n. However, we have already proved that the perimeter of the infected region cannot increase, and therefore, this is impossible. Let's move on to the next problem. We begin with the number 19 raised to the power 100. Then we add all its digits to obtain a new number, which we call x1. Next, we add the digits of x1 to get another number, and we continue this process until we are left with a single digit. The problem is to determine that final digit. Pause the video here if you want to give it a try. Here's the solution. The sum of a number's digit is invariant under modulo 9. We prove this claim for a 3-digit number, and the same argument extends to numbers with more digits. Consider a 3-digit number and write it in its expanded form. Then separate the sum of its digits from the rest of the expression. Observe that the remaining part is divisible by 9. Therefore, the remainder obtained when dividing the original number by 9 is the same as the remainder obtained when dividing the sum of its digits by 9. So, we just need to compute 19 to the power 100 modulo 9. There are many ways to do this. We will use the binomial theorem. Write 19 to the power 100 as 1 plus 18 raised to the power 100 and apply the binomial expansion. Every term except the first is divisible by 9. Therefore, the remainder is 1. Let's move on to the level 8 problem. We have an n by n square grid. We fill each cell of the grid with either 0 or 1 in such a manner that the sum of numbers in each continuous 2 by 2 subgrid sums up to 2. For example, if we consider a 4 by 4 grid, then each of these subgrids must have a sum equal to 2. So, what are the number of ways we can fill up the n by n grid? Pause the video here if you want to give it a try. Suppose we fill the first row. Notice these two columns. The values in the next row for these columns must both be 1. Similarly, the values in the subsequent rows for these two columns also get fixed. Now consider this 2 by 2 subgrid. 3 values are already fixed, so 4th value is also determined. By the same logic, the entire grid gets fixed once we fill the first row. However, this holds true only if the first row is not alternating. If the first row is alternating, then there are exactly 2 possible ways to fill the next row. Either you fill it with 0, 1, 0, 1, and so on, or with 1, 0, 1, 0, and so on. The same logic applies to all subsequent rows. Each of them can be filled in 2 ways. So, in this case, we will have 2 to the power n minus 1 options to fill the grid after the first row is fixed, unlike the previous case where there was only one way to fill the entire grid. Hence, if the first row is alternating, there are 2 to the power n minus 1 ways of filling the remaining rows. There are 2 ways to make the first row alternating. You can start with either 0 or 1. Hence, the total number of grids with the first row alternating is equal to 2 to the power of n. If the first row is not alternating, there is only one way of filling the remaining rows. We can fill the first row in 2 to the power n ways, and exactly 2 of these are alternating. So, there are 2 to the power n minus 2 ways to make the first row non-alternating. Hence, the total number of grids with the first row non-alternating are 2 to the power n minus 2. Hence, the total number of grids is 2 to the power n plus 2 to the power n minus 2, which is equal to 2 to the power n plus 1 minus 2. Let's move on to the next problem. We have a 7 by 7 matrix where each entry is a number from 1 to 7. Additionally, there are 2 constraints. Each column must include each of the numbers 1 through 7 exactly once. For example, the first column contains each number from 1 to 7 exactly once. The same is true for other columns. Let aij represent the entry in the ith row and jth column. We must have aij equal to aji for all I and j between 1 and 7. For example, these 2 elements are equal. Similarly, these 2 elements are also equal. Now these elements form the main diagonal of the matrix. The problem asks, what is the probability that each number from 1 to 7 appears exactly once on the main diagonal? Pause the video here if you want to give it a try. Let's start with simpler cases. For example, consider 2 by 2 matrices. If we construct matrices that satisfy the two given constraints in the problem, we find that none of them have both 1 and 2 appearing exactly once on the main diagonal. If we construct 3 by 3 matrices, we find that all of them have 1, 2, and 3 appearing on the main diagonal. Similarly, if we construct a few 4 by 4 matrices, none of them have the numbers 1 through 4 appearing exactly once on the main diagonal. If we construct a few 5 by 5 matrices, all of them have the numbers 1 through 5 appearing on the main diagonal. This might lead to the suspicion that in odd-sized matrices, all numbers will always appear on the main diagonal, whereas in even-sized matrices, it is impossible for all numbers to appear simultaneously on the main diagonal. So for a 7 by 7 matrix, the numbers should always appear in the main diagonal exactly once. It turns out that our suspicion is correct. Let's prove it. Fix a number k between 1 and 7. Because every column contains each number exactly once, the total number of times k appears in the matrix is exactly 7. Alright, now observe that if k appears outside the main diagonal, it must occur in pairs, as each occurrence must have a corresponding counterpart symmetric to the main diagonal. So every occurrence of k off the main diagonal must appear in pairs. In other words, k must appear an even number of times outside the main diagonal. Now we have established that k appears exactly 7 times in the matrix. So k must appear an odd number of times in the main diagonal. This is true for all k between 1 and 7. Therefore, each number from 1 to 7 appears an odd number of times in the main diagonal, which means every number from 1 to 7 must appear exactly once in the main diagonal. So, the required probability is 1. Let's move on to the level 10 problem. We roll a fair 6-sided die 10 times. Let n sub I denote the number of times side I appears. Compute the expected value of the product of the random variables n1 through n6. Here's the solution. Note that the random variables n1 through n6 are not independent, as their sum is always 10. Therefore, we cannot express the required expectation as the product of the expectations of the individual variables. For each roll I from 1 to 10, let AI denote the variable which is equal to 1 if roll I shows a 1 and 0 otherwise. For example, if only the third and fifth rolls show 1, then A3 and A5 are 1 while all the other AI are 0. Similarly, let BI denote the variable which is equal to 1 if roll I shows a 2 and 0 otherwise. In the same way, we can define the variables CI through FI corresponding to roll values 3 to 6. Note that the number of 1s in the 10 rolls is equal to the sum of AIs. Similarly, the number of 2s in the 10 rolls is equal to the sum of BIs and so on. So the product of the variables n1 through n6 can be written like this. If we expand this, we obtain terms of the following form, where the subscripts I1 through I6 can each vary from 1 to 10. Now notice that if any two subscripts are equal, that term must be 0. For example, consider this term. At least one of A1 or B1 must be 0, since the first roll can be either 1 or 2, but not both. So this term must be equal to 0. Similarly, any term in which at least two subscripts are equal must be 0. So we only need to consider terms where the subscripts are distinct. Let's call the terms with distinct subscripts good terms. The number of such good terms is simply the number of permutations of 10 objects taken 6 at a time. Now let's calculate the expected value of each good term. This time, the individual variables are independent, so we can express the expectation as the product of their individual expectations. Moreover, each individual expectation is equal to 1 by 6, since the probability of each outcome on a roll is 1 by 6. So the expectation of each term is 1 by 6 to the power 6. Now consider this product again. When we expand it, we obtain some good terms with distinct subscripts and some other terms. We have already proved that all the other terms are equal to 0. Each good term has expectation equal to 1 by 6 to the power 6. Therefore, the expected value of the entire expression is equal to the number of good terms multiplied by the expectation of a good term. This evaluates to 175 over 54. Alright, now a bonus problem for you to try. 10 points are marked on a circle. A frog starts at one of these points. Each second, it jumps randomly to one of the two adjacent points, either clockwise or anti-clockwise with equal probability. So, what is the expected time for the frog to visit all 10 points? Post your answers in comments. Hope you liked the video. If you want to learn how to solve these kinds of interview problems, we invite you to check out our course, Quant Interview Masterclass, where we teach you how to think when solving difficult problems. We also cover the entire theory, specifically tailored for quant interviews, along with over 1,000 problems. Thanks for watching and see you next time.